And we're going to be talking about bonding, and I think that you're going to find that this is not very different than what we did in Honors Chem, just a little bit more with some of the exceptions and just a little bit more depth, but pretty similar to what we've already learned about. So there are three basic types of bonding. There's ionic bonding, there is which are simply electrostatic attractions between ions. There's covalent bonding, where sharing of electrons is involved in a molecule. And there's also metallic bonding that happens in a metal. Let's say you have a sheet of iron. Is you have you have the nuclei lined up. You have atoms sort of in a crystal lattice, just like they would be in a solid. But the electrons that go with those are mobile. They're called a sea of electrons. They don't stay with their own specific nucleus. And this fact that these electrons are able to move is what allows metals to be electrically conductive and also heat conductive. Okay, so we call that a sea of electrons. That's a term that might come up in the AP test. So three types of bonding: ionic, covalent, and metallic. And metallic just refers to a metal bonding with itself. So you know ionic bonding, right? It's like, let's say you have a sodium atom, and this sodium has 11 electrons, and it's got just one in its valence shell. It's going to give up that electron so that it loses that outer shell, and it only has 8 in the outer shell. It becomes nice and stable, loses an electron along with some energy. And then there's a corresponding chloride atom that has 7 in its outer shell, 7 electrons in its valence shell, and it wants to pick up an electron in order to also become more stable, to get a full stable noble gas configuration. And so the sodium loses an electron and the chloride gains an electron. It becomes a full positive and a full negative charge. And then what holds these together in the crystal lattice is this full electrostatic charge, plus charge on the sodium, minus charge on the chlorine, holding them to each other. If we remember back in thermodynamics, we said that or even in our periodic table lesson, we talked about ionization energy, and we said it takes 495 kilojoules to remove an electron from sodium. So it takes energy to remove these electrons, and even though it's close to the octet and it becomes more stable, it still takes energy to remove them. And we also saw that chlorine, when chlorine gains an electron because of its electron affinity, it loses energy and becomes more stable, so it loses energy here. But yet, if you look at this reaction, and let's actually watch a little video of this reaction.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
Okay, so when we look at that, what we see is a really exothermic reaction, and the question is, why is it so exothermic, this coming together of this crystal? And the third piece of the puzzle, besides the energy taken to take an electron away from sodium, or the energy lost when chlorine adds an electron, it's this whole lattice energy. So lattice energy is the energy required to completely separate a mole of a solid ionic compound into gaseous ions. So the reverse of that is the energy that's lost when the ions come together to form a lattice. So it's this big reduction in energy because this lattice is very stable, very low in energy. So this lattice energy is the third piece of the energy puzzle that results, in this case, in a very exothermic reaction when we make this ionic compound or salt. So let's take a look at lattice energy. So again, these are energies required to separate the ionic compound in the lattice and make these go off as a gas. So let's take a look. We've got a bunch of ionic compounds, and we have kilojoules per mole of energy required to break those apart. So what do we notice? What are some of the trends you might see? Well, one of the things you should see is all of these ionic compounds have a positive ion that's a +1 and a negative ion that's a -1. And what we have here is a positive ion of +2 with a -1. Here it's a +2 with a -2. And here we have a +3 with a -3. And what we see is as we go from a +1, -1 and increase the charge, the lattice energy goes up. So the stronger the charge of the ions, the closer held those ions are to each other. Okay, so here where we have +3, -3, have the greatest energy of all. Now the other thing we can look at is we can look at, let's say, lithium chloride, fluoride, and iodide. So if we look at fluorine, chlorine, and iodide, as we go down this row or this group in the periodic table, what's happening here is this ion is getting larger, right? I'm adding another shell. These are getting larger. So the distance between the lithium nucleus and the chlorine nucleus are further apart. So they're less tightly held. So it's less energy for a larger ion than it is for a smaller ion. So the smaller, as you can imagine, the more those nuclei in the charges get involved in holding that lattice together. But the biggest impact is the impact on the charges. So lattice energy increases with two things. The first and most important is increased charge of the ions, and the second thing is decreasing size of the ions. So this energy is associated with Coulomb's law. If you remember electrostatic energy, there's some constant, and it's Q1, Q2. Those are the charges, right? Charge on the positive, charge on the negative, divided by D, which is the distance between them. Okay, so this is why if this is a +1, -1, this is going to be a smaller electrostatic energy than if this was a +2, -2, right? Okay, so let's take a look and try to apply this. So we have sodium fluoride, cesium iodide, and calcium oxide. So let's first look at the charge, because the charge itself is enough to make a difference. So I want to get my pointer working here. I have in this case, a +1, -1, +1, -1, +2, -2. So this will be the strongest, right? This is the highest. And here I have, these are both +1, -1. So let's take a look at the comparison of the ion size. So sodium fluoride compared to cesium iodide. Cesium is bigger, right? Sodium is smaller. And iodide is also bigger compared to fluorine. So this is going to be higher than the cesium iodide. So this would be the lowest, second lowest, third lowest, or highest. Okay, let's take a look at these. So this is a +2 with a -1, a +2 with a -1, a +2, and a -2. So this is going to be the highest right here. And if I compare these, both have fluorine, but there's a difference between magnesium and calcium. So magnesium is smaller. Calcium has another shell. So this is going to be stronger. So it's going to be 1, 2, and 3.